Hello everyone. Today we are going to explore two fundamental concepts in financial economics, arbitrage and the stochastic discount factor or SDF. These concepts form the backbone of modern asset pricing theory and help us understand how financial market function. I'm Lavanya Parikh and this presentation is a course project in the course ECO672 Dynamic Optimization at IIT Kanpur. Throughout this lecture, we'll try to develop a cohesive understanding of how these two concepts are linked and why they matter for both theoretical finance and practical applications. Let us begin by understanding what arbitrage is. So, so arbitrage at its core refers to the simultaneous purchase and sale of an asset to exploit price differences for risk-free profit. This is a foundational concept in finance that helps us understand market efficiency. So this statement looks a bit kind of vague. It looked vague to me, but yeah, this an analogy will definitely help you understand it better. So I offer you this analogy, a student-professor analogy, where a student and a professor plays a game. They both play a game, and so the game is as follows. They both take in turns to ask each other questions, and for every unanswered question, the person who cannot answer it has to pay some amount. But the catch is, professor pays $1 for unanswered questions, and student pays only $0.5. So there exists a risk-free profit via asymmetric rules. So student can earn risk-free profit infinitely by asking unanswerable questions, very vague questions, or the questions which no one can answer. So this is a state where an arbitrage exists, or a game where an arbitrage exists. So the formal condition for arbitrage is, you can see, is if Rx is greater than equal to 0, then we must have Px greater than equal to 0, where R is the payoff matrix and X is the portfolio vector. P represents asset price. In simple language, I guess you can say this is that if a portfolio has non-negative payoffs in all future states, it cannot have a negative price today. If it did, that would constitute an arbitrage opportunity. Now we'll look at efficient markets and no arbitrage. So why does arbitrage matter so much in finance? It's directly connected to the efficient market hypothesis, which states that prices reflect all available information. In efficient markets, arbitrageurs immediately exploit any mispricing, driving prices to their correct levels. Think of it, I guess you can think of it this way, that if an asset is underpriced relative to its future payoffs, traders would continuously buy it, and which would drive this its price up until the opportunity disappears. Similarly, for overpriced assets, the overpriced assets would face selling pressure until their prices correct correct to the no arbitrage condition. In this example, which is generally called an FX triangle, where you can where generally an arbitrage opportunity exists between three currencies. You can exchange your dollars for euros to pounds and then back to dollars, and you can kind of earn a profit if there exists an arbitrage opportunity. So now we will mathematically formalize and kind of understand what that Rx greater than equal to 0 and Px greater than equal to 0 business was. So our key condition remain the same. If Rx is greater than equal to 0, then we must have Px greater than equal to 0. where R represents the payoff matrix with dimensions, states, cross assets. We'll see in the next slide what the states and assets, how they are represented. And X is our portfolio vector, which has long and short position in assets. It's kind of weights you assign to your assets in your portfolio. And P is the price vector of these assets. So interpretation, we can say that if Rx is equal to greater than equal to 0, we are stating that our portfolio has non-negative payoffs in all possible future states. And when we say that Px is greater than equal to 0, we are stating that such a portfolio cannot have a negative cost today, where Rx is greater than equal to 0. I mean, if a portfolio is giving you non-negative payoffs in all the states, there cannot exist a portfolio such that its price is less than or equal to 0. I mean, less than 0. Sorry. Yeah. So formal breakdown of all the matrices and the equation which we saw here, it goes like this. So each row of R matrix represents payoff in a particular state. So each row, again, it shows the payoffs in a particular state, and each column represents an asset. And the multiplication Rx gives us the portfolio payoff across all possible states. It makes sense, right? You multiply the portfolio weight to the asset, and then you get your returns in all the states over all the assets. So under no arbitrage principles, if Rx is greater than equal to 0, that means always gains, then Px must be greater than equal to 0. I mean, you have to always pay upfront. So a violation example would be if Rx is equals to 10 and your Px is equal to 0. I mean, you are getting returns of 10 and your cost for that portfolio is minus 10. That, I mean, doesn't make sense, right? It does make sense, but you're getting risk-free profits again, if this kind of situation ever existed in some market. So again, back to our students rigged game. In this game, the student creates a setup where the professor must pay $1 for every unanswered question, while the student only pays $0.5. Okay, so from a portfolio perspective, we can view this as follows, which you can see on your screen. Asset 1, student asks, where the payoffs are +1 and price is -1. And asset 2 is when professor asks, the payoff is -0.5 and price is 0.5. And you can formalize in our equation this game in our equations of Rx and Px as follows. And Px is also not it's a dot product, not a matrix multiplication. So you can see that Rx is greater than equal to 0 and Px is negative. So definitely arbitrage exists, and student always earns a profit when he asks a must-lose question, which is an unanswerable question for the professor. Yes, so now we'll formulate no arbitrage problem using linear programming. We can approach the no arbitrage condition through the lens of linear programming. The primal condition or no arbitrage condition can be formulated as minimizing your P dot x and subject to Rx greater than equal to 0. Px is obviously your Px is your portfolio cost. So you need to minimize that subject to positive returns. Yep. So in an arbitrage free market, the trivial solution to this problem would definitely be x equal to 0, which is cost equal to 0. And in any portfolio which had px less than 0 with rx greater than equal to 0, and arbitrage opportunity would definitely exist. This is powerful because it shows that no arbitrage is fundamentally a constraint on the relationship between prices and payoffs. In other words, you can say prices in market cannot be set arbitrarily. They must conform to certain restriction to prevent arbitrage opportunities. So you might have guessed what will come next. Yeah, the dual of this problem. So the dual of our primal problem has a kind of a fascinating result. It was fascinating to me. Um, the dual of our primal problem is maximize 0 over all state prices, subject to pi r is equals to p, and where state prices are always greater than equal to 0. I'll explain what pi means now. So the interpretation of this dual problem is kind of profound or fascinating, as I mentioned. The dual variables pi can be interpreted as the price today of a pure state contingent payoff, essentially what it costs today to receive $1 if and only if a particular state occurs tomorrow. Yep. The equation pi r equal to p implies that the price of any asset is the sum of its state dependent payoffs weighted by these state prices pi. So by duality theorem, if the primal has a finite solution, which it does in arbitrage, where x was equal to 0, then the dual must have a feasible solution. This leads us to a crucial conclusion, that is the existence of a non-negative vector pi satisfying p is equals to pi r is equivalent to the no arbitrage condition. So this is kind of a bridge to our next topic, the stochastic discount factor. We'll see in later slides why and how this pi links to SDF. Yeah. So now we'll see what stochastic discount factor is. This section would introduce you to the stochastic discount factor, which is a fundamental concept in modern asset pricing theory. The SDF helps us understand how financial markets value different payoffs across different economic states. You can think it as of a tool which connects today's prices with tomorrow's uncertain payoffs. We'll learn how this concept relates to the no arbitrage principle, which is a cornerstone of financial economics. So the key equation and definition now. We are exploring what SDF actually is. Think of SDF, which we denote by M, which is a random variable, as an exchange rate, and but instead of converting between currencies, it converts future payoffs into present values. The key equation we see here is P is equals to expectation over mx, shows that an asset's price today equals the expected value of its future payoff multiplied by the discount factor. Here x is the future payoff of some asset, and m is obviously our SDF, and p is the price of that asset. What would you price it today? Yeah. So the interesting part is that this exchange rate varies depending on the economic conditions. For example, the intuitive analogy example here, when the SDF is equals to 0.9 in an economic boom, it means $1 received during the good economic times is worth only $0.9 today. But when the SDF equals 1.2 in a recession, $1 received during economic bad times is worth $1.2 today. This actually reflects the fundamental idea. that payoffs in bad times are more valuable than the same payoffs in good times. We can also to the state prices, link SDF to the state prices through the equation pi s equals to ms into probability of that state happening. This equation essentially says that your state price pi s is equals to um, your our SDF in state S and probability of that state happening. Um, our analogy for this would be like here state prices actually represent the cost today of receiving $1 if a specific economic state occurs in the future. So now we'll look at a simulation of SDF versus our asset price. So this is a geometric Brownian motion simulation, the code to which I have attached in the description, and there are multiple other code blocks as well which you can explore related to arbitrage and SDF. So the primary key takeaway from this simulation is the blue line, which is our SDF, and the red line, which is our asset price, are inversely related. That when the SDF fluctuates over time, our asset prices move in the opposite direction, which indeed confirms the inverse relationship between asset prices and SDF. Now we'll derive the state-based consumption SDF. First step to which is defining our representative consumers optimization problem, which is our consumer maximizes the future expected consumption based utility um, from time period t equal to 0 to infinity, and this e naught is expectation at time t equal to 0, and our choice variables are consumers choice variables are how much to consume, how much will he consume in each period t, which is ct, and obviously there is beta, which is our discount factor, like, and then there will be our intertemporal budget constraint, which is which is step 2 in defining the problem. Here it is, which is our future wealth is equals to our returns on the savings in the previous period. This essentially says that our budget constraint, and the first after deriving our Euler equation from the first order condition, it comes out to be this. I haven't done the whole algebra and whole Lagrangian thing, but it's fairly easy to do it. But we are more interested in what these results mean. So this U dash CT is the marginal utility of consumption today, how much happiness one more dollar gives you right now. And this whole expectation, the thing inside expectation gives the expectation conditional on today's information. So that CT plus 1 is actually state dependent, because we don't know how much like what tomorrow how much we will consume, because it's all state dependent. So the economic meaning of this is the left side explains you the pain of saving $1 today and lost utility from not consuming it, and the right side is expected gain from investing that $1, earning RT plus 1 returns and consuming tomorrow, and discounted by beta because it's in future period, one future period ahead. So using the definition of SDF, which is MT plus 1 is equal to beta into ratio of the marginal utilities. Um, so the beta here penalizes future utility for impatience, and like SDF is SDF is kind of a crisis multiplier. $1 during a recession when you're poor might feel like $1.2 today. And the previous exam intuitive analogy, just keep that in mind. That and if during a boom you are getting $1, which would feel like $0.9. So okay, MT plus 1 is equivalent to beta times ratio of marginal utilities. So if our future consumption drops, that is bad times, economic recession. That means our U dash marginal utility from one more unit of consumption would go up, and hence our SDF would also increase. So the asset pricing relation comes out to be, after substituting for MT plus 1 into the Euler equation, replacing U dash CT, we get expectation of MT plus 1 RT plus 1 is equals to 1. Result, which is our asset pricing relation. The interpretation for this would be, for any asset with returns RT plus 1 and the future returns, its risk adjusted expected returns is equal to 1. This essentially ensures no arbitrage, and all assets are fairly priced relative to their risk. And to give like intuition on why does this all matter, and it's kind of an intuition builder, we can think of, let's say a recession hits and our future consumption goes down, expected future consumption goes down, then our marginal utility for future consumption will go up, and that means our future SDF would increase. That would essentially mean that assets paying in recessions get higher valuations today. That makes sense. Yeah. Also consider a risk-free asset. Let's say it pays RF returns in each period. So let's say if okay, we can replace RT plus 1 with RF, and we can rearrange the equation, and then it will look like expectation of M is equals to 1 by RF. So if our expectation of M goes up, then RF goes down, and vice versa. So this explains why there are low rates in crisis and high rates in economic booms. Yeah. So now we look at how can we derive the fundamental equation of CAPM from SDF. So first off, we'll assume a linear SDF, which is given by this. Interpretation of variables would be that A is the base discount factor, which is a time preference component, and B is sensitivity to market returns, and RMT plus 1 is gross return of market portfolio. And why is it linear? It simplifies the relationship between the SDF and market returns, and it captures the idea that investor dislike assets that perform poorly when market does. um, yeah. So the analogy for this would be, think of SDF now as a market risk meter. So if the market RM rises, if RM rises, MT plus 1 decreases. So the future payoffs in good times are less valuable today again. And the opposite would be, if market crashes, MT plus 1 spikes, payoff during crisis are highly priced. So now risk-free pricing condition. um, as discussed previously, if let's consider any, let's say, a bond, a government bond, it pays you RF returns consistently irrespective of what period we are in. We can take it out of expectation, and our fundamental asset pricing, this final asset pricing relations is still satisfied. Yeah. So now we can find out what the values of what is the value of A, and so it essentially, the variable A, it essentially means that A adjusts for both time value of money, which is 1 by RF, and compensation for the market risk, which is B times expectation of RM. So pricing any asset, and this is whole lot of algebra, and after a few steps, we'll finally also we'll have to introduce a few variables, which is beta, and there's one more lambda somewhere. Yeah. So this, after a few lines of algebra and replacement, we finally get our CAPM, fundamental CAPM equation. Yeah. So interpretation of all these variables would be better given in a CAPM course, which I will try to attach in the future readings. And but yeah, we can assume this. The key takeaway from here is, we can essentially assume a linear stochastic discount factor and end up getting the fundamental equation of asset pricing. So now we'll look at how stochastic discount factor connects to no arbitrage. Will explore the connection between no arbitrage and SDF. In an arbitrage free market, there must exist state prices pi s that correctly values asset across different economic states. The SDF is directly related to these prices through the equation which we already have seen, but this is a more generalized way to, I guess, write it. So this relationship ensures that all the assets are priced consistently according to P is equals to expectation of MX, and when this holds, there are no free lunches in the market. You can't make risk-free profits without investing. The SDF effectively captures how the market values pay off differently depending on the economic state. Let's just once revisit our old game. So this slide actually applies our theoretical framework to a practical example of the old student professor game. In this game, there are two types of actions, um, when student asks and when the professor asks a question. So from a portfolio perspective, if there is one round of each type, the student has a net gain of zero point 0.5. The SDF perspective helps us understand that in an efficient market, prices or discount factors would adjust to eliminate such free profit opportunities. The existence of a valid SDF ensures that there are no arbitrage opportunities. So essentially, if there exists no if there exists an SDF, there will be a condition where no arbitrage will exist. So now we'll look at an example. It's a very simple example. So let's see the SDF framework in action, I guess. With a simple two-state world, we have boom with 0.6 probability and recession with 0.4, and the SDF values are 0.9 and 1.2 respectively in each state. and there's this some stock which pays you 120 in economic boom and 80 in economic recession. So when we calculate the price, which is the expectation of m into the payoffs and the probability, so it comes out to be 103.2. So the key thing to note here is the that this pricing reflects both the probability of each state and how the market values payoff in different economic conditions. Notice that the recession payoff is given more weight per dollar, that is 1.2 versus 0.9, despite being smaller, reflecting the higher valuation of money during bad times. So now we'll see why are arbitrage and SDF linked. This slide would clarify the fundamental connection between arbitrage and SDF. So the no arbitrage principle ensures that there are no free profits in the market, while on the other hand, the SDF provides the mechanism that discounts future payoffs according to their state specific values. If arbitrage was possible, investor could get money for nothing. The SDF prevents this by ensuring the pricing formula P equals to EMX holds for all assets. Conceptually, no arbitrage guarantees the existence of state specific prices, which, when scaled by probabilities, form the SDF. The SDF then consistently prices all the assets, ensuring the market remains arbitrage free. This elegant connection shows us how pricing consistency and absence of arbitrage are two sides of the same coin. So now we'll come to the key takeaways and practical implications of arbitrage and SDF. As we near the end of this lecture, let's highlight the key insights. Arbitrage is the concept that you cannot make risk-free profits without investing. Markets quickly eliminate such opportunities. The SDF is the tool that translates future uncertain payoffs into today's prices, accounting for both time value and risk consideration. In an efficient arbitrage free market, the SDF exists and satisfies P equals to EMX for all assets. This framework is fundamental to pricing financial instruments like stocks, bonds, options, and derivatives. Understanding how the SDF and no arbitrage work together helps explain market pricing and efficiency. Now, the concluding remarks. To conclude, we have seen that no arbitrage principle prevents free lunches by ensuring fair pricing, while the SDF provides a mechanism to discount future payoffs according to state specific values. Together, they offer a unified framework for asset pricing. This approach underpins many asset pricing models like CAPM, Black Scholes, which I have not discussed, connecting market behavior with investor preferences. Understanding this linkage explains market efficiency in the long run. In essence, the SDF is the language of risk and time. It ensures consistent pricing across assets, eliminates arbitrage opportunities, and binds the market together. This framework helps us understand why assets are priced the way they are, and how market maintain efficiency. So, also I have attached the whole, as might have mentioned in during the lecture. I've attached the course handout. You should go through it. You'll understand the reference. You can go through the references which I've used, and a few simulations which I will attach. And yeah, that's it. Thank you.